Welcome to Math 331, Lecture 20, first lecture after the Red Sox have triumphed and won the World Series with a very impressive 11-3 record in the playoffs, I believe. So what I want to do today is actually something that was inspired by visiting my daughter's 4th grade math class, where they had a rule for divisibility of 7 that I've never seen before. And so before we get to other stuff, I want to know why this rule is true. So I actually saw her teacher at Stop and Shop later that day and told her, "You've ruined my weekend because I'm now going to be thinking about this problem for days," or trying not to think about it, because I've never seen this divisibility rule for 7. But I want to leave it for my problem-solving class so we can attack something live that I do not know the answer to. The best way to phrase this is they had a chart on the board of divisibility rules. And they didn't have 11, so I gave them 11, which is a fun rule. How many of you have ever seen Euclid's axioms for geometry? It's classic Sesame Street. One of them is not like the other, but one of these just doesn't belong. Which one?
Like parallel?
Yeah, Euclid's fifth, the one on parallel postulates. All the other ones are really nice and straightforward and simple. And then you have this long monstrosity, which is the fifth postulate. And in fact, there are geometries where the fifth postulate does not hold. And this gives you the geometry on a sphere. So on a plane, if you have two parallel lines, they don't intersect. But on a sphere, two parallel lines can intersect twice. You can talk about points of infinity, maybe. And there's other types of geometry. There's planar geometry, but you can have obtuse and acute geometry as well. So let's do divisibility rules. So what we'll do is we'll do number and we'll do rule. All right. What's the first one we should do?
1.
Yeah, okay, so we could be 1. So the divisibility rule of integers by 1 is pretty straightforward. It's divisible. 2.
1's digit is 2.
I'm sorry?
The 1's digit is
Right.
2.
So ends in 0, 2, 4, 6, 8. Or the 1's digit is divisible by 2. Either one of these is a fine. 3.
Digits add up.
So digit sum is congruent to 0 mod 3. How many of you have not seen this divisibility rule before? If you want to see if a number is divisible by 3, you add the digits. And if that number is huge, then you add the digits of that and you keep iterating. And the reason is you can write 10 as 9 plus 1. You can write 100 as 99 plus 1. You can write 1,000 as 999 plus 1. All of these numbers are multiples of 3. So if I gave you the number, say, A1, A2, A3 as its digits, this would be 999 A1 plus 99 A2 plus 9 A3 plus A1 plus A2 plus A3. And so what we would have is this number is divisible by 3 if and only if this number is divisible by 3, because this part over here doesn't matter. I'm just going to see if there's a good piece of chalk hidden. Can you check all the way down and see if there's a good piece of chalk? Yeah, yes, there is. Okay. All right, so this is divisibility by 1, 2, and 3. What number should we do next?
4.
We could do 4, but given that this is on the board, 9. So I'll put 9 in parentheses, and then just put the parentheses there. So it makes sense to do 9 right now. Okay. Next one is 4. What's 4?
Last 2 digits?
Yeah. Last 2 digits are congruent to 0 mod 4. So if the last 2 digits are multiple of 4, or what you could do is you could do divide by 2 again. All right, 5 ends with a 0 or a 5. 6.
3 and even?
Yep. Rule 2 which is essentially what you said. It's got to be even, and it's got to have the digits sum too. Okay. 7 we're going to hold off on for 8. Last 3 digits. And the reason is that 100 is not a multiple of 8, but 1,000 is. And so is 10,000, so is 100,000. So you only need the last 3 digits. So last 3 digits congruent to 0 mod 8. 10 ends with 0. And I'm curious, how many know 11?
I know multiplication. Like, for 2-digit numbers, I know. Like, if you multiply 11 to like 12, you like separate and then add. So it's 132.
Okay, and if that was the question I was asking, then that would have been a terrific answer, yes. But that is not the question being asked. The question is not being asked how. Now, again, there's a lot of people, Professor Benjamin at Harvey Mudd is phenomenal at doing fast mental arithmetic. And there are ways to quickly multiply numbers or square numbers or stuff like that. So being able to multiply numbers by 11 is a good skill to have. But that's not the question I'm asking here.
Is it like if you add up the first and last digit, they need to be the same as second and second to last?
No. But you're close. So it's alternating sum is congruent to 0 mod 11. And so the idea is 1 is congruent to 1 mod 11. 10 is 11 minus 1 is congruent to negative 1 mod 11. So every time I multiply by 11, 10, so every time I multiply by 10, 10 is negative 1 mod 11. So if I now look at 100, that's going to be 10 squared, which is going to be 1 mod 11. 1,000 is going to be negative 1 mod 11. So if I give you a number like, A1, A2, A3, A4, this is going to be congruent to, the first one would be negative, positive, I think. Yes. Negative A1 plus A2 minus A3 plus A4 mod 11. Because what we're doing here is we have A1 times 1,000. That's A1 times 1,000 is 11 minus 1 cubed. And all that really matters, because I'm looking at things modulo 11, is the negative 1 cubed. Everything else, when I expand, is going to have an 11 somewhere inside. So this is the rule for 11. 11 is just alternating. Okay. So we have every rule now but 7. Okay. Has anybody ever heard a rule of 7? I will keep that in focus for just a little bit. So I guess we've got 1, 2, 3, 9, 4, 5, 6, 8, 10, 11. Here's rule for 7. Double the ones digit. Take number, remove ones digit, subtract the doubled ones digit, is this 0 mod 7. So for example, 511. The doubled ones digit is 2, so I do 51 minus 2 is 49, which is congruent to 0 mod 7. So 511 should be a multiple of 7, and if I go into 511, 7 times 7 is 49, and there you go. So this is the rule for divisibility by 7. And for those of you who have seen the Sesame Street, one of these things is not like the other. One of these things just doesn't belong. There is another way to get a rule for 7. It's even worse than this rule. Which of the previous rules could we convert to a rule for 7? It won't be an exact perfect conversion, but we can modify the idea behind one of these rules. But it'll just be more complicated. There were only 2 choices before. Now we're going to have more choices.
11.
Yeah. How would we modify the rule for 11?
You change 11 minus 1 to 7 plus 3.
Yeah. So what we could do, and this is bad, is 10 is 7 minus 3. So 10 is congruent to negative 3 mod 7. 100 is going to be congruent to negative 3 squared, which is 2 mod 7. And you keep going down like this. And you would have, yes, exactly, you would have that kind of weighted sum. What do you think might be easier than doing that weighted sum?
Divide it by.
Yeah, it might actually be easier to just try to divide by 7. But I mean, if you were to write a computer program and you had a huge number, which would be easier to do the long? I think this would still be better long term in terms of digit operations. But for small reasonable numbers, it might be easier just to divide by 7 than trying to remember what those coefficients are. So again, this is one of the advantages of being the professor, is you get to have some say in what the class is. This was just begging for an explanation. And again, nothing against how they're doing math in the elementary school. I am going to at some point try to explain to them why the rule for 3 works. I might have a private special meeting with Cam and Kayla on Wednesday to start practicing that. So when you are teaching 4th graders, it's perfectly fine to have a couple of rules, but it's nice to be able to give some sense of why they're true. So even if you can't explain the rule for 7, if you can explain the rule for 3, maybe you can then make people understand where it's coming from, that math has a way to prove things like this. Or start with the rule for 2, or the rule for 4, or 5, or 10. Start with rules where you can explain it and then say, hey, we can do this with a little bit more work, with some more advanced machinery. There's more stuff we can do. All right. I have been resisting all temptations to think about this problem for several days. Fortunately, the Red Sox have been kind enough to have some very long games where I have basically been a mental vegetable and unable to do anything while watching for things to be refreshed and updated because I was watching online, because I was at a meeting. Anybody have any thoughts as to how the hell we should start proving this rule for 7? So again, I have deliberately not thought about this. The idea is, how do you attack a problem like this? What would you do as your first step? And I've just come up with what I think is a natural first step. It may not be the best at the end of the day, but I think it's a good first step.
Consider the doubled ones digit.
Okay.
Mod 7? Or?
Sure. So what kind of numbers are you going to be looking at initially?
Some numbers between 1 and 18, I guess.
Sure. I mean, I would have actually just done a 1-digit number. Does this work for 1-digit numbers? And then if we can do it for 1-digit numbers, then maybe try to do 2-digit numbers. So let's assume n is 1 digit. So we start off with n. The double is 2n, which is going to be from 0 to, as you said, could be as large as 18. And then we look at n minus 2n, which is negative n. No, sorry. We look at 0. Sorry. We look at 0 minus 2n, which is negative 2n. when is negative 2 going to be a multiple of 7? I'm sorry? Yeah. As negative 2 is relatively prime to 7, and 7 is prime, this is a multiple of 7 if and only if n is. All right, so we've done it for one-digit numbers, yes?
Coprime is all we need, right? Like it doesn't matter that 7 is prime.
Coprime is the same as, yes, it doesn't matter that 7 is prime, correct.
Okay.
So if we had a number like 10, well, 10 wouldn't work here, sorry. If we had a number like 15, yes. Okay, so again, this may not be the best way to go, but at least this is starting to give us some intuition and some feeling. Now, what's the next number we should look at? Yeah, two-digit numbers. So now let's try n is 2 digits. So how do you want to write n?
A1, A2.
I'm sorry?
A1, A2.
Yeah, we'll write it as A1, A2, which is 10A1 plus A2. All right, and then the double of A2 is going to be in 0 to 18. And now we look at A1, A2 minus 2A2.
A1
Sorry, just A1. Sorry, just A1. I keep doing this. Just A1. And then it would actually be 10A1, right? No, it would just be A1. It's just A1. So we lose the 10. All right. Now this looks a lot more involved. So the question is, what would it mean if this is a multiple of 7? So we might want to look at negative 2 in a nice way.
Minus A2, minus A2.
So what's the multiplicative inverse of negative 2? Mod 7. So negative 2 times 5 is negative 10, which is the same as positive 3. No. Negative 2 is the same as 5 mod 7. Okay. I said multiplicative inverse. No, right. No, that's fine. So if negative 2 is the same as 5, what is the inverse of negative 2? So what do I need to multiply negative 2 by to get 1 mod 7?
Oh, yeah. 3.
3. So 3 times negative 2 is congruent to 15 mod 7, which is congruent to 1 mod 7. So 3 is the multiplicative inverse. So that means that our expression here, A1 minus 2A2, is that the same as 3A1 minus 6A2? Mod 7. Yes or no? No. I can't just multiply by 3, right? So,
you shouldn't have. I was like, why did we do that? That didn't, like I was saying, like that didn't work.
right. So I can't just multiply by 3 and say that these are the same. But if I multiply this by 3, does this change whether or not this is a multiple of 7? No. So this is definitely true. I can multiply by 3. The reason I want to do this is I can rewrite negative 6A2 as what? As plus A2. So this is the same as 3A1 plus A2 mod 7. What should I do to the 3A1? What is this beginning to look like? 3A1 plus A2. It's looking a lot like 10a1 plus a2. It's not. How does it differ from 10a1 plus a2?
By 7.
Oh, but it doesn't matter.
So this is the same as 3 plus 7a1 plus a2 mod 7, which is the same as 10a1 plus a2 mod 7, which is the same as n mod 7. So the idea is, if we multiply -2 by 3, we get 1 mod 7. So we take our expression and we multiply it by 3. That's fine. It's not going to change whether or not our number is a multiple of 7. So we then end up getting n mod 7, and now we're done. So as 3 is relatively prime to 7, doesn't change if a multiple of 7. Again, I have no idea if this is going to work in general, but I just want to show you how I would attack a problem I've never seen before. Most of the time in this class, well, when you ask me things, I love it when you ask me things, hey, I'm curious about the following, because then it's new for me as well. I have been doing a lot of these problems longer than you've been alive. I've had my no, I don't think I've had my PhD longer than you've been alive yet, but I've definitely had my undergraduate degree longer than you've been alive. So for some of these problems, I can't help but knowing how to attack it. One of the whole goals of this class is to teach you guys methods and perspectives and techniques so that when you see something new, how can I frame this in terms of things I've done before? So one thing is, well, let's look at the other divisibility rules we have. Maybe some of those will give clues. Don't think it really helped this time. Then let's look at maybe special cases. And so I'm a huge fan of trying special cases. And by looking at some special cases, looking at the 1-digit number, okay, well, that was so special, it really wasn't a problem. But looking at the 2-digit, again, I have no idea. I'm just gambling right now that it's going to work. But it seems likely that something like this is going to work. And we can see 10 is 7 plus 3. And so using this deep result, we now begin to see why we want to put in this doubling and subtracting. And now we're chopping things off. So when we have our number, we're removing the a2, and so we're dividing that almost by 10 and shifting. Well, when we add 7, we then shift it back. And then we're then restoring things to where they belong. All right, shall we try a 2-digit number or go straight to the general case? I know what I would do. I've been flying, I've been changing time zones, I was up late. If it was me, I would probably just do a 3-digit number now and just really get intuition done. And then when you write things up nicely, you make it so that nobody can understand what you're doing. You just do the general case, and you give no hint to the audience as to what is going on.
Didn't we already do the general case? Isn't like 10A1?
So I think that this argument should work for the general case. We've technically only proved it for a 2-digit number.
But there's no restriction that A1 is, is 1 through 9.
That's beautiful. That's beautiful. Yes. Probably the only time this hat will be off today. Okay? Yes. Yes. So I can't go into details because I don't want to make the person known, but I was visiting a colleague, and her husband is also a mathematician. And we had done enough math for the day. They had a young kid. We were playing with the kid. And he was working on a math paper, and we were making too much noise because he was trying to do a calculation. It shouldn't be that hard, but we were just too distracting, so he left the room. He comes back and I'm like, yeah, it was trivial. Are you going to include the proof in the paper? No, it's trivial. Are you going to sketch the proof? No, it's trivial. A footnote. It took you an hour to figure out how to do this. You had to leave the room because we make too much noise. This is sadly how math papers are written. They often remove all the exploratory work that gives you a sense of what's going on. They remove the settings and they just go straight, boom, 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 like machine gun line of attack.
I'm actually a little bit curious. So we have 10A1 plus A2, and like that doesn't have any restrictions on like necessarily what A1 and A2
Right.
are. But so say like you
Ah.
make A2 like 18,
So-
right? But then the actual ones digit is not.
So
18.
so what if we made A2 the last two digits?
Right.
So let's try that. So what I'm going to do here is I have a Mathematica notebook open, 43 times 21. Oh, it shouldn't take this. Oh. I had printed out a image for, okay, it's 903. That's a little bit too small. So let's do 413 times 21. So let's do 8673, which is a multiple. Well, let's make it a little bit better. 86583. So this is a multiple of 7. So what you are saying is we should be able to double the 83 and subtract that from 865. So 865 minus the double of 83 would be 166. Oh, wonderful. If that was 866, we would subtract off 166, which would be 700, right? So this should be 699. I'm a little worried.
It doesn't work. 9 times 7 is 63.
Well, I'm saying 700 is a multiple, right?
There we go.
So,
my arithmetic has really been awful.
well, I think it's all linked. The injury, I think, has. No, so this is actually high-level arithmetic, and in some sense, if you look at Common Core, they actually want kids to look at something like this. If you want to divide 7 to 699, divide 7 to the closest multiple you can. And it doesn't have to be the closest, but the closest one that you can think of, and then correct. So have we made a mistake here? I think it doubles to 166, and I will double check 865.
I mean, even just like a simple example of like 49, if you just choose it to like be 2 times 10 plus like 20, like it doesn't end up working.
Right. Okay, so the question is, can we still use the attack to prove it with just doubling the one digit? What happens if we double 2 digits? Well, so here, did we ever use the fact that A2 is a single digit number?
No, but we made the A2 or the A1 into a 10. But now we have to make it into a 1.
Right, but I'm saying if we wanted to double the A2, the problem is now A2. Oh, wait a minute. So we just doubled the digit A2. Maybe we need to double 3 times the second digit. Maybe we don't treat each digit the same when we're doubling. Because A3 is 8 times 10 plus 3 times 1. And so when we were doubling things, maybe we should view this 10 as 7 plus 3. And then write this as 8 times 7 plus 8 times 3 plus 3 times 1. And now, 8 times 3 plus 3 would be 26? 27? I did that on purpose so that you would not feel bad. So that would be 27. Right? So let's try that now. So if we double 27, that should be 54?
Yep.
That's a good subtraction. 1, 1, 8. And now we want to divide that. Well, so it doesn't work. Oh well. I was going to say, you can immediately go with 700, you're left with 111. 111 is a multiple of 3. It's not going to be a multiple of 7. So sadly, that did not seem to work. So we'll be leaving this then, I guess, as a question of, is there a way to fix what's going on in that case? So let's try your approach of just doing a general number. So n is going to be equal to a1 times 10 plus a2. So we'll see if we ever use the fact that a1 is a one-digit number. I don't think so. We look at a1 minus 2 times a2. Yes?
Well, I guess when you write n as a1, a2,
Mm-hmm.
like on the left, like
Yes.
before that, a1,
Yes.
a2, right? And then if you make
We've got to be careful here, because over here, that doesn't mean we're multiplying a1 and a2.
right, but you're saying that a2 is the number in like this digit,
Yes.
right? And then if you say like a2 is like 17, for example, like can you like is that?
Well, that's why I was wondering if what you do is you convert a2 to just whatever it should be mod. So here, what was the number we were doing a moment ago? It was 86583. What if you looked at 83 mod 7? So that would be the same as.
Oh, I think. Sorry.
That's 6 mod 7.
But I think the problem is that we can't use. We're going to 865. We should be using 8650 because we're multiplying that by 100. See, 865.
Oh.
If 865 is A1, then it should be 100 A1. So if we use 8650. So what we're calling A1 is 865, which we multiply by 100, not 10, in n.
I see. So the issue we had before was we were multiplying by 10, and now we want to multiply by 100.
Yeah.
So we should really be multiplying by 3 squared, maybe.
Yeah.
So maybe should we, instead of doing minus 2, should we do multiplying it by 4? Because we need to do 2 3s. So what if we did?
I guess the question I had was kind of different from what we're doing then.
Okay.
Like my question wasn't if you have like a longer number, but if you have like say like 49,
Right.
and you because a1 and a2 can be anything, if you let a2 be like 29, and let a1 be 2.
Right.
But isn't that different than just saying like make the number bigger and then take the last 2 digits, right? It's like literally, it's just like taking a different number.
Yeah, so I mean here we were shifting our a1 up, so we would want to do it by 3 squared if we had to leave off 2 digits. So when we're looking at this stuff over here, I almost think that this should be a minus 4. I mean a minus 2 times a minus 2, which is a plus 4. And 9 times 4 is 36. So if I take 83 and multiply that by 4, I get 332. If I subtract that from 865, I get 533, which is not a multiple of 7. So the question is, do we have to take the 83 and look at this as 8 times 3 plus 3 and work with 27? So if we do 27 times 4, that's 108. So then if we do 865 minus 108, that's 757. And that's not a multiple either. All right, so we'll leave this as I'll leave this as a nice extra credit as to, is there a way to do it? What would be the rule if you want to just use the last 2 digits? It feels like there should be something. Let's try to prove the general case right now, though. But again, this is exactly what you should be doing. And I will make this worth 2 homework problems if you can come up with a rule with 2 digits. And you can either have that in exchange for other problems, because you're taking something that's been done before and you're asking new questions. This is the best way to create new mathematics. Because you know somebody already gives this could be heard by my daughter's class, so I would say, somebody already cares about it. Right? One of the hardest things when you write a paper is to motivate who cares. I often have my students referee papers for journals, and I remember one year, the 2 students came up to me and said, Professor Miller, we're a little, the paper you gave us, there's only 6 references, and they're all by the 2 authors of this paper. Right, and what can you deduce from this? No one else cares? Yes, no one else in the world cares about this. They can't relate their work to anything else. And no one has cited their papers. It's entirely self-contained. So if you have something that's already been published, if you have something that people already care about, to try to make the point that somebody should care about what you're doing, you're already at a huge advantage, right? Because somebody already cares. So if you take this rule for 7, if you can find a generalization with the last 2 digits. All right, so let's look at this. We have A1 minus 2A2. Now, we can look at 3 times A1 minus 2A2, which is going to be congruent to A1 minus 2A2 mod 7. Right? Because if I no, it's not going to be congruent. It's going to be the same divisibility. Right? Because when I multiply it by 3, I don't change the divisibility. So now this is the same as 3A1 minus 6A2 mod 7. And this is the same as 3 plus 7A1 plus A2 mod 7. This is the same as 10A1 plus A2 mod 7, which is equal to, or can use my number n mod 7, and we're done. So your observation works. There was no need to do the 3-digit number. So we will then leave it as an exercise of how to handle the case of removing the last 2 digits. My feeling is that we want to be multiplying by 3 squared. And so it should somehow be, but maybe it's going to be something for the first digit. Maybe it's -2 for the first digit and maybe 4 for, I don't know.
I think I have it.
Okay.
But it's kind of silly. It was what he said.
Okay.
It would just be, so A2 is 2 digits.
Right.
It would be 10A1 minus.
Okay, so we want A1, A2.
A2, where A2 is 2 digits, and A1 is any number of digits.
Okay.
It would be if 10A1 minus 2A2 mod 7 is divisible.
All right, so that's the condition. So, okay, so before we had.
Let's turn it into the other one.
Yeah, so.
I mean, we could turn that 10 into a 7 to at least clean up a little bit. I mean, a 3.
Yeah, but I would much rather multiply by 10.
That's actually true.
But of course, as a professor who could assign things, so we now multiply the 865 by 10,
Yeah,
and get 8650 minus twice 83, which is 166, and then that's 8484 divided by 7. That's looking good. That's okay. All right.
I think I have a different rule too.
Okay.
If you double the 865 and then add
Double 865. Okay.
that's actually kind of fun.
Yes. All right.
And then add 83.
Okay. Now, if I multiply this by 3. Oh no. Okay. All right. So you wanted to do this. Okay. So
1730.
and then we're going to add 83. All right. So 1813.
Yeah, it works.
Okay. So now the question is, I want to, because, okay, I think I know why this works. Is it because of 50?
That's not how I did it.
Oh, okay. So I was looking at 100 is 50 times 2, which is 49 plus 1 times 2. And so now, if I look at 86500 plus 83, this is going to be congruent to 865 times 2 plus 83. So we can generate lots of different rules. And this is exploiting the fact of 49. So basically what this is doing is you're taking the 865 and you're just putting the 0 on instead. That's not that bad. So the question is, if you had to do the arithmetic, which would you rather do? So by having A2 have more digits, this has fewer digits. So if I give you a really long number, this might actually be a better rule. Because you could try to equalize. If I gave you an 8-digit number, maybe I'll take 3 or 4 digits for A2, and now my subtraction is going to be smaller, and that'll be a smaller number to look at. So how many of you have heard of the 3x+1 problem?
It was on Project Euler.
It was on Project Euler. So we are not going to get to the Conway checkerboard problem today. That's so two of my favorite quotes about this problem is Kakutani used to talk about this when he traveled and gave talks at other departments. And people would say, oh, it's not that bad. And then they'd spend about a month and give up in frustration. And I think he referred to it as a Soviet conspiracy to slow down American mathematics. Because the problem seems so simple to state. Erdős said mathematics is not yet ready for problems like this. So here's the rule. an plus 1 is 3an plus 1 if an is odd, and it's an over 2 if an is even. Or what you might do is an plus 1 is 3an plus 1 over 2 to the k, where 2 to the k double divides 3an plus 1. So the double divides means 2 to the k divides it, but 2 to the k plus 1 doesn't. You pull out as many powers of 2 as you can. Somebody give me a reasonable number, not too big. I think we've done this in this class before, and I've told you what number not to say.
24.
Yes. So do not say that, because 4 is not too bad. So 4 is even, so we divide by 2 and get to 1. 1, we then multiply by 3, and we just loop back to 1 for all eternity. So give me another number.
2 to the 5 million.
You had so much goodwill in class. But 2 to the 5 million, that's not bad. So we'll just do any power of 2 collapses through 4 straight to 1. So how about 11? So 11 is odd, goes to 33, 34, goes to 17. 17 is odd, goes to 52, which becomes 26, which becomes 13. 13 goes to 40, which is 5. When I pull out things, 5 goes to 16, which then goes straight to 1. What do you think the conjecture is? Yeah, it always terminates in 1. It's amazing how many people have tried to prove this and have failed, and how little we know about this. So I do have a paper on 3x+1. I felt almost compelled as a number theorist to have some result in the subject. Let's say you want to work with a 100,000 digit number. So from a computational point of view, how would you work with a 100,000 digit number? This is going to exceed the long in C by quite a bit. What kind of operations do I need to do on my number? I just have to multiply by 3, add 1, and divide by 2. So what you do is you store numbers as arrays. You can have extremely long arrays without any trouble. And then if you want to add 1, it's easy to add 1, and you just march down the array. So if you have your array like this, if you want to add 1, you add 1 here. Do I have to carry? If yes, continue and go like that. All right. Is it easy to multiply by 3? Yeah, to multiply by 3, I multiply by this by 3. If I have to carry, I carry, then I multiply by this, and I just march down. All right. What about dividing by 2? So what would you have to do if you want to do division by 2? You have to start over here now and start playing these games, right? Do you know how you can divide by 2 by multiplying?
Multiply by half.
Yes, you could multiply by a half.
I think that deserves another cat.
No. What number should I multiply by? It's similar to what we were doing before. By 5. So multiply by 5. That's easy to do. And then shift by dropping the ones digit. Because if you want to divide by 2, if you multiply by 5, and then if you chop off the last digit, that's the same as dividing by 2. So you can actually work with huge numbers without much trouble.
Could you do it in like binary instead?
Yes, and in fact, you should do this in binary, right? You should not be doing this problem in base 10. And in fact, there is a famous problem by Cole. I will try to remember to send you, where he proved a certain factorization, and he actually just wrote down the products, multiplied them out, and got the number that people were wondering, is it prime or not? And as a joke, I've suggested to students over the years, if we just write this multiplication in base 2, can we get a really bad journal to accept it? So I will try to send you some notes about that. This is a good place to start.